Today I talk about mathematical morphology in geosciences and geospatial data sciences. This geospatial data sciences is also called as geographic information science. And these geosciences and geospatial data sciences, we encounter many different geometrical structures. And as a definition, like mathematical morphology is a theory and a technique for analysis and processing of geometric structures based on set theory, lattice theory, random functions. And so this field is more European, but it has number of applications in geosciences and geospatial data sciences. And you will see that this I have prepared it, and when we talk about a spatiotemporal model or understanding a spatiotemporal behavior of a specific geoscientific phenomenon, we talk about acquisition of the data and then further retrieval of information from that data, and then characterization of that particular information and reasoning of that particular information, and then modeling, simulation, visualization. All these are ingredients of a kind of spatial data sciences. And all through have actually used digital elevation models, which is a kind of a spatial data where the variable is specifically the elevation value. So billions of dollars was spent on generation of digital elevation model for across the globe, and then I should say that it was not well utilized by the people, and because I see that digital elevation model is like a black box, and it has lot of hidden geometric, topologic and morphologic information. And then if someone knows a kind of mathematics like mathematical morphology or wavelets or fuzzy set theory, and they can really look at the DEM with a different perspective, and there are many features which are hidden can be really retrieved, and then further we can work on the behavior of those particular features, how they are behaving across the time periods. And I could see that mathematical morphology is an area of geoscience that most people don't realize will literally change the way they look at Earth and Earth-like planets. And particularly I am talking about the terrestrial surfaces and planetary surfaces. And in entire mathematical morphology, it is like you have data and you have another data with which you will investigate and then unravel various different hidden topological properties of that particular terrestrial data. So the data is, I am calling it as, there are different types of data representations. Are you talking about a map like a binary data, or you are talking like a spatial field like a digital elevation model? And there is a B, which we call it in mathematical morphology as a structuring element, with which you can actually investigate the main data to unravel various features, and that B can be designed and defined at will as long as there is a proper justification. So in one quick slide to show you, and I was talking about the retrieval, quantitative characterization, quantitative spatial reasoning, and then modeling, visualization, and I will show in entire thing. And this is about the retrieval, and you have a specific data which is a synthetic digital elevation model from which the unique topological networks are geophysical networks, valleys which are nothing but the rivers that we see, and then ridge connectivity networks, and these two networks are very important when we actually characterize the terrestrial surfaces. And then the digital elevation model can be partitioned into watersheds in a hierarchical manner. There is a watershed, there is a river basin, there is a watershed, there is a sub-watershed, there are still sub-watersheds, and that hierarchical partition and how we do it, and we actually carried out with respect to mathematical morphology. And then that is one aspect which you will see in the further slides. And there is another one, and so not every time we want to actually characterize the terrestrial surfaces in terms of the networks that we derive, and we have a classical morphometric schemes, and they actually give the network analysis, and out of morphometric analysis we derive two very important topological quantities which we call them as bifurcation ratio and mean length ratios. Using those two topological quantities we can characterize the terrestrial surface, and those quantities are not just sufficient, and we had to give some other shape based analysis, and how we have given that it is actually based on the morphological shape decomposition. That is another case, I will show it further. And then we have the roughness characterization, and we have a specific morphological granulometries, which is nothing but looking at the data at a multiple spatial scales. And so to do that, and how we actually employ multiple morphological operations, multi-scale morphological operations to find out how a specific spatial field is diminishing its energy and then how it is gaining the energy. We have come up with some kind of quantities called morphological entropies, and they are a spectrum of roughness values that we can compute. It is not just the global roughness value, but we can compute how the roughness value is from left to right, top to bottom, and then in all possible directions, and how we can compute with that spectrum of roughness values. We have certain applications. Of late somebody was talking about uh, fault surface roughness, and fault surface roughness would actually indicate, do we have a large number of aftershocks or minimal number of aftershocks. It's the aftershock number is related to the roughness of a terrestrial surface, and so that is another thing. And so why roughness value computation is very important. And then subsequently the another case I would show a kind of morphing, and we see in highly time varying and slowly time varying phenomena in a terrestrial surface. One example is probably the floodplain surfaces, and where the floodplain sand dunes are very highly time varying and across certain short time periods, and you see the changes in the terrestrial the floodplain surfaces, and taking those surfaces at a different time instants, and how actually that surface has traversed from source to target. And so for that we have given some nonlinear morphological interpolations, and so that too also I would show it in further slides. And so this is what is the quick overview and the spatial data, and I actually talk about threshold elevation regions, mostly like we call in geography as the spatial objects, and the spatial fields like digital elevation models, where you have multiple grayscale values, and each grayscale value represents an elevation value, which we actually represent within a normalized scale of 0 to 255, where it is easy for us to represent a pixel value with 8 bits per pixel, and then 255 stands for the peakest region and the 0 stands for the mean sea level. And so such normalized digital elevation models and have been generated of late by following various different remote sensing mechanisms, interferometric analysis, radar grametric analysis, and spot stereometric analysis. And at the same time there are many uncertainties in those digital elevation models. I still believe the topographic map which was created by going in a field survey and generated a digital elevation model generated out of a field survey based thing is much more accurate than the digital elevation model that were generated out of remotely sensed data, because there is a paper called not all DEMs are equal, and so when they are not equal, and so when we process and analyze them, and at the end results, are we really what we derive is really accurate enough to really follow in our spatiotemporal models. And then the next one is mathematical morphology. I don't show those notations and equations and transformations, but to tell you that there are two fundamental morphological operations. One is erosion to shrink and dilation to expand. These two, erosion and dilations, were actually derived from Minkowski operators, Minkowski sum and Minkowski subtraction. And the basic difference between morphological operations and Minkowski operations are the B in the structuring element in Minkowski operations are symmetric in nature, but whereas in morphological operations, and they can be derived, they can be designed in a multiple, the asymmetric forms, and then we can derive various different transformations out of it. And some of those transformations will show in the next slides. But this one, out of many morphological algorithms that we developed and demonstrated for specifically for geoscience and geospatial data sciences applications, and I would show the skeletonizations, morphological skeletonization for retrieval of information from digital elevation models, and morphological shape decomposition, morphological granulometries, and then distances, morphological distances, and morphological interpolations. I will see to what extent I can cover within the stipulated time. And then, so this is a kind of education piece that we have written a few years ago. The digital elevation model, as I mentioned, billions of dollars were spent in generation of digital elevation models, and then they are really underutilized. If someone has a specific knowledge like in mathematical morphology or some kind of mathematical field, the way they look at digital elevation model is entirely different. So this is a synthetic digital elevation model. This is our Cartosat digital elevation model, And so this is shuttle radar topographic mission digital elevation model and its vertical exaggeration, and these are the bathymetric maps and the bottom topographic maps, and then there actually the vertical exaggeration shown, and these are a large number of even Chandrayaan DEMs, and I have seen the optical high resolution camera based DEM from Chandrayaan 2 was really remarkable. It's just 25 centimeters resolution we have. You can see the pebbles and rocks on the moon surfaces, and so that is a very interesting thing. But so how to employ those things, and when I mentioned digital elevation models and then relevant mathematics and then science out of that particular DEMs, and we have geometric, morphological, topological quantities, and I have listed a lot of features that one can derive from digital elevation models, and which I don't spend more time on this, but a few things I will show. And mathematical morphology, these are the two founders, co-founders, Georges Mathurin and who was considered as a father of geostatistics, and Professor John Serra, his first PhD student, and who is considered as father of mathematical morphology. And incidentally, Georges Mathurin was the student of Professor Paul Levy, who is the father of probability. And there was another student of Paul Levy was Professor Mandelbrot, and who was the father of fractal geometry. And this is just an information, right? So as I mentioned here, these are the fundamental operations: morphological erosion to shrink, dilation to expand, opening, which is a cascade of erosion followed by dilation, and closing, which is cascade of dilation followed by erosion. And these are all nonlinear operators. And then using those operations, fundamental operations, four operations: morphological skeletonization, morphological shape decomposition, and granulometries and morphological interpolations were developed, and then subsequently we applied them in the first thing is extraction of the skeletal network from the digital elevation model. What is the skeleton? The skeleton is just the river network that one can actually derive from the digital elevation model at the terrestrial surface. And so this is actually like a spatial function, and which where brighter regions are higher elevation regions and darker regions are lower elevation regions. And then you can actually see that there is a kind of network that is flowing, and which is like local minima values. So there were some studies earlier using some Newton's descent property, and they were extracting the networks, but the same ideas were not working on, they're working fine on the terrestrial fluvial regions, highly hilly terrains. But whereas when you come to the tidal regions, and those actually the descent property based frameworks are not working, and in turn what we have done, and taking the skeletal network of the contours, that we threshold decompose them by following a simple piecewise threshold decomposition, and we can decompose them into maximum of 255 threshold decomposed elevation regions. And from each of the thing, and by following the skeletonization equation, that is where you have nth scale erosion, and that nth scaled eroded version is smoothened with respect to the morphological opening with an arbitrary size b, and then from this we typically you get the skeletal subsets of order ranging from 0 to capital N, and taking the union of all those skeletal subsets you get a network like this. And from all threshold decomposed elevation regions which are in binary form, and if you extract these skeletal networks, and if you stack them in a systematic way, you get a typical river network from the entire terrestrial surface. And so the dual of that network is that ridge connectivity network. For that you can either inverse the transformations: instead of erosions you perform dilations, instead of opening you can perform the closing, and then you get the ridge connectivity networks, or conveniently you can invert the digital elevation model and then apply the same skeletonization principle, you can get the ridge connectivity networks. Those things are shown here. This is the digital elevation model, and green lines are valley connectivity networks, and blue lines are the ridge connectivity networks. Further, this watershed transformation, and which I am not going to stress it here for want of time, but that watershed transformation is it works like a drop off principle. It is like when you have some regional minima at a randomly placed locations, and then treating them as the water bodies, and you allow those water bodies to flood, and where exactly they extinguish each other, and then you construct a dam, and that is the principle involved in the watershed transformation, and then from which you can actually partition that given terrestrial surface into their watersheds in a hierarchical manner. So these are all some of the fractal things, and we have decomposed them into their corresponding topological elevation regions within which, and then by showing that is a vertical exaggeration, and you can actually simulate the landscapes. And so the question is, can we really simulate the landscape which is typically mimicking the realistic landscapes? It is possible by tuning the boundary conditions and the characteristic information of the structuring element, that is B, that I have been showing in some of the equations. So that is the first part, and the second part being the morphological shape decomposition. As I mentioned, so there were some terrestrial analysis, quantitative terrestrial characterization by following some age-old very classical methods like morphometric analysis and hypsometric analysis, and those ideas were actually implemented on the river networks, and there is a specific order designation, and then after the order designation is done on the river networks, and they compute the three topological quantities as I mentioned. So they are bifurcation ratio, mean length ratio, and mean area ratios. Using those ratios, they used to tell that and what are the conditions of the terrestrial surfaces. So are the conditions supporting a kind of percolation of water, or the less water percolation, there is a lot of water going as a runoff, and there are various characteristics they used to derive it, but are they really sufficient? And so as I look at over the period, and that probably demands some other mathematical field to really study the terrestrial surfaces in much better way. So this morphological shape decomposition is nothing but decomposing a, let us see, this is an Apollonian space, and this could be decomposed into octagons of various sizes, and it is like a decaying of the Apollonian space, and then so I will further quickly go, and then you can see how it is these things were packed with a square like B, and so this is rhombical like structuring element, this is octagon like structuring element, and their interfaces you can see it. This is the idea, and we have followed here, and so these are three networks given here. All these three networks are topologically invariant in terms of the morphometric topological quantities that I was referring. And but what a core geomorphologist wants is, it is not just the topological invariant parameters, but they want what is that parameter which can show the basic distinction between these three networks. In turn, what we have done, and we have ignored the networks, we subtracted the network from its corresponding basin or a convex hull, and whatever is the subtracted version is actually the fat fractal, and you pack that fat fractal with the morphological decomposition, something are like this. This is the network, and its corresponding closed hull is this, and you, after subtracting the network, and you have the white space which is actually called hill slopes in terms of geosciences, and then you pack that space with non-overlapping disks of various different types, and then you compute the a number and a radius relationship, and what we get is the not just the scaling invariant parameters, but also the shape dependent parameters. What we want at the end is not just the scale, but also the shape. So shape matters a lot, and so that is another thing. And this the third case being the granulometric analysis, and what we do, this is a digital elevation model. So as you keep on performing erosions and followed by dilations with an increasing size cycle, and you keep seeing that this this particular landscape is losing its energy, and it is with different cycles. This is gaining energy when you are doing the converse, that is dilations followed by erosions of different cycles. And so this loss of information is typically called a pattern spectrum here, and then total area of that particular what is the total energy is nothing but the sum of all the elevation values, and then you derive that, and then you get a kind of probability like value, and the p log p for different cycles, and sum of all those p log p values would get you the morphological entropy, which is a roughness value. So here you realize that all these B's are symmetric B's, and when you choose some asymmetric B's like a directional structuring elements, and you can see these are the structuring elements that I have used, these are the structuring elements I have used, and when we use the directional structuring elements like these are the four directions we have shown, and we can compute the directional roughness values in which direction the roughness value is very high, and so what is its indication? Why so in specific direction roughness value is more, and perhaps it is very vulnerable to any perturbation. I think one more small case is there, if you allow me, and I will just show it. So the distance part I will probably skip, but so this interpolations is morphological interpolations. You can see what is that we can gain out of this interpolation equations on a binary case. And so sparse data can be made into the denser data by hierarchically interpolating the intermediary contours, and this is for the binary case, whereas this is for the spatial fields. When you look at these are the two spatial fields in between, you can actually compute the interpolations. It's a hierarchical way, and then so with this probably I'll just end my talk. And so if there are any questions, and I want to show this particular conclusion, mathematical morphology is an area of geoscience that most people don't realize will literally change the way they look at Earth and planets. And these are some of the books that we have written using our results. And so the question is topological data.
Yeah, basically, if you have observations from random topological space, how to estimate say things like Euler characteristics, Beatty number, etc. So do you think this will help in mathematical morphology? It seems.
Yeah, we had about the topological analysis, but we didn't do anything much. But there are relationships between mathematical morphology and topological analysis, particularly the granulometries. So granulometries actually follow a kind of rolling ball mechanism. When you have an irregular surface, when you roll a ball within inside,
Right.
what are those regions which could not be reached by this particular ball, and you just filter them. In the same way, when you roll it from outside, and what are the regions that they could not reach, and by increasing the size of the ball and how actually those regions were not covered. So when you are rolling inside and when you are rolling outside, and I think that study was actually done by the same group which proposed this topological analysis.
Okay.
Yeah, so this is one connection I can give, but I know that I have not answered your question properly.
Talk to Yogesh. He knows a lot.
I know Yogesh. Yes. Yeah. Thank you very much.
One more question.
Yeah, it's more of an application. I was just wondering your DEMs. How is it applied to some of the Indian context in terms of in recently in the Uttarakhand Joshimath, you had certain depressions and all that. So you also mentioned that probably the remote sensing is not so accurate yet, but I saw some results of the remote sensing. They are sort of showing that there are a few meters of depressions in 100 years. So are there any similar attempts from your DEMs?
Yeah, so these DMs are the same DMs from where they actually gave those inferences, so from Joshimath region. And I am not saying actually they are inaccurate, and because different DEMs derived out of different mechanisms. Some DEMs, like by taking the satellite data, which is through optical sensors, and if you generate a DEM, and the DEM that you get will also give you the height of the tree on top of the terrestrial surface. And there is a lot of anthropogenic activity, but what we want is, it is not just the tree height. We want actually the ground level elevation. So for that, actually interferometric radar based techniques are there, and they are highly accurate enough. But even now we have drone based DEMs they are deriving. They are very, very accurate, and we can really compare them with contour based DEMs by means contours that I meant are actually the contours actually mapped from physical surface.
Do you also think that the spectral thing also can improve? Because for the Chandrayaan 2 again,
yes, yeah. Spatial resolution can be improved, and but that is what. And if really young people can be taught about the relevant mathematics, and the way they look at this spatial data is really remarkable. It's entirely different how actually I studied and how the younger generation can really look at. Thank you very much.
Thank you. It reminds me of a CAT scan at the terrestrial level.
Yes, sir.
Okay. Well, please join me in thanking Dr. Daya Sagar.